Hi, I am Ryan Currier. I am part of the Mountain Hydrology Research Group at the University of Washington. I'm going to introduce the energy budget equation and how it relates to rain-on-snow flooding events. During a rain-on-snow flooding event, we have a period of heavy rain and melting snow. The heavy rain contributes most of the water in a flooding event, while the snow can account for up to 25%. During a typical storm, we have snow high in the mountains and rainfall at a lower elevation. Therefore, thanks to snow, we have less runoff during a precipitation event. However, during a rain-on-snow event, atmospheric conditions change and we have a new warmer air mass come through. The warmer air mass doesn't reach its freezing point as quickly as the other air mass did. Therefore, we have a new snow line that is higher in elevation and a larger area contributing to runoff. Note that we now have snow exposed to warm and windy weather as well. So there are two common misconceptions about rain-on-snow flooding. The first is that the rain is actually washing away the snow, and the second is that the warm rain is melting the snow. However, when we actually calculate the amount of energy in the rain and look at an extreme event, say 5 inches of rainfall at 10 degrees Celsius, we get less than an inch of water melted from the snow. So if the rain isn't melting the snow, then what is? Well, you need energy to melt snow, and you need exactly 334,000 joules to weaken the hydrogen bonds and melt 1 kilogram of ice. So where is this energy coming from? To answer that question, we have to take a look at the energy balance equation, and there are 6 different components to the energy balance equation. From left to right, we have solar radiation, long wave or terrestrial radiation, sensible heat, latent heat, energy from rain, and energy from the ground. On a sunny day, the main component to the energy balance equation is solar radiation, and a lot of the energy that is received by the snow is then reflected because of snow's high albedo. Terrestrial radiation is emitted by anything that has a temperature, including you and me, and even clouds and trees. Terrestrial radiation is typically less than the solar radiation term, but can still be important. For instance, on cloudy days, radiation is absorbed by the clouds and re-emitted more efficiently back towards the snowpack than on a clear day. Sensible heat flux is especially important during warm and windy conditions, as energy is being transferred from the warm air to the cool snowpack. Latent heat flux is especially important during warm, windy, and humid conditions because the water vapor from the humid air will condense as it moves over the cold snowpack and releases latent heat, which melts the snow. And finally, you have the ground heat flux, which is the transfer of energy from the ground to the snowpack, and this term is usually much smaller than the other components of the energy balance. So the sum of all 6 different energy components that we just discussed control the amount of energy available to melt the snow. Knowing which conditions matter the most during rain-on-snow conditions are critical for understanding snow's contribution to flood forecasting. You can explore the importance of each energy balance component through an Excel snow model by clicking on the link below.